This video is for Unit 2.3/4 Similarity Shortcuts. There are three main similarity shortcuts, and this is number one, and it's called the angle-angle postulate. And what our similarity shortcuts tell us is if we can identify that these shortcuts are true for any two triangles, then we know the triangles are similar. So the first shortcut tells us that if two angles of one triangle are congruent to two angles of another triangle, then the two triangles are similar. Now, if you think about this, this makes sense because we only need to prove that all three angles of a triangle, that one angle is congruent to one, the second to the second, the third to the third. And if two triangles have congruent angles, we know they're similar. What we might remember here is that this third angle, in this case L and Z, we know whatever L is, it's got to be 180 minus J and K. Therefore, L and Z are the same on these two triangles. So let's do an example of when we might use angle-angle similarity. We're given two triangles, we're given some information about them, and we're going to determine if they're similar. For each triangle, we have one angle, but we can figure out some other information. So we know that if this is 106 degrees, this angle on the bottom triangle must also be 106 degrees. And that's because we have vertical angles. So we've got that each triangle so far has one angle is congruent to the other. So now we need to know something about the other angles. On the bottom triangle, we're given angle Q is 36 degrees. So if we can find that one of these angles is 36 degrees, then we'll know the triangles are similar. So what's really important to note here is that these lines are parallel, and I can tell that with these markings on both the lines that they're parallel. So if they're parallel, I always want to be on the lookout for some of those special angle pairs. And what I have here and here are alternate interior angles. So if you kind of ignore that extra line, you can see that Q and M are alternate interior angles, where line QM is the transversal, and lines LM and QP are our parallel lines. So we know that angle M is also equal to 36 degrees. So now we have two triangles. That have two angles that are congruent. So that's an example of angle-angle similarity. Now we know the third angle is also congruent because it's 180 minus 106 and 36 together. All right, so the last thing we're asked to find here is the measure of MN. So remember, when we have similar shapes, their corresponding sides are proportional. We know that the side MN corresponds with this side QN, that's 20. And the reason we know that is that side MN is between the 106 degree angle and the 36 degree angle. So it's included between those. Similarly, QN is included between the 106 and the 36 degree angle. So we're gonna know that these two sides here are corresponding sides. So when we go to set up that relationship, we know that whatever MN is, I'm just going to call it X. The ratio of X over 20, because I'm comparing MN to QN, that's going to have to be equal to another known ratio. And we can get the similarity ratio for these two triangles from these two sides that are corresponding. So this must be equal to 33 over 30. Once we write our proportion, we can cross multiply. There might be other ways to solve this, but it's always safe to cross multiply. When we cross multiply, we get 30x equals 33 times 20, which is 660. Divide both sides by 30. And we get that x is equal to 22. So the length of side MN is 22 units long. You will be asked to do some similarity proofs in this unit, so let's look at an example of one. Here we're asked to prove that triangle WVX, so WVX, is similar to triangle WZY. Now, if we can use any of our similarity shortcuts, we can prove they're similar, and we've only learned about one of them, so that's kind of what we should be on the lookout here for. So if I go to kind of like my thinking space, I'm going to say thinking. I'm thinking that I don't have any labeled sides, so I'm just looking at angles. And I know that I need two congruent angles to use the angle-angle similarity. So if I look, I already have that angle V is congruent to angle Z. They're both 90 degrees. And I'm just kind of thinking ahead. That's given to me from the picture. I might write over here that it's given. I also notice that both triangles have angle W, and it's the same on both triangles. Like if I sketched one out to the side of the other, they would both have this exact same angle W. And so I know that W is congruent to itself. And I know that when something is congruent to itself, that's an example of the reflexive property. So I think I'm ready to do my proof. I know I put my statements on the left, so I start with my givens. I'm given that angle V is congruent to angle Z. Sorry, that's supposed to be a congruent symbol. And that is given. And then I know that angle W is congruent to angle W, and we said that's because of the reflexive property. So if I can establish in my proof that there's two pairs of congruent angles, corresponding congruent angles, then I can now say that triangle WVX is similar to triangle WZY. And the reason for that is the angle-angle similarity. Technically, it's a postulate, but if you can remember angle-angle similarity, I'm okay with that. All right, this is our second main similarity shortcut, and it's called the side-angle side similarity theorem. So if an angle of one triangle is congruent to an angle of a second triangle, and the lengths of the sides, including these angles, are proportional, then the triangles are similar. So remember, including means that the angle is between the two sides. So if angles A and P are congruent, side AB over PQ is equal to AC over PR, so these sides are proportional, then we can use this shortcut, and we don't need to even know angles B and C or Q and R or the lengths of side BC or QR. So let's just look at an example. Let's say that AB is 5 units long and that 15 for AB, that PQ is 5. And then let's say that side AC is 18 units long and that PR is 6. So we already know that these angles, I'm putting A for angle here, we already know that our angles are congruent because we're told that from our picture. So I could check and I could say the ratio of AB to PQ, so 15 to 5, must be equal to the ratio of AC to PR, which is 18 to 6. And we could check this with our cross products, or I could realize that both of these simplify to 3 over 1. So they are in fact proportional. So here's an example of side-angle side similarity. What value of x makes triangle ABC similar to triangle DEC? So we have to look carefully. We already have vertical angles. So I know that these angles are going to be congruent. All right, so we've got vertical angles. And we know that from our statement that if ABC is similar to DEC, that means that sides, I could think that side AB over DE is equal to BC over EC is equal to CA over CD. All right, so if I look at what I'm given, I don't know anything about ED or AB. So I'm going to just cross that off because that's not going to help me at all, and that's not going to help me use side-angle side similarity. So I do know that this statement must be true. So the thing that I'm missing from this is CD. I don't know what CD is, but I can replace CD with the variable x. So now if I fill this out down here, BC over EC, so BC is 54 over EC, which is 18, must be equal to CA, which is 36, over CD, which is our unknown. So now I can solve this with cross multiplication, but something that might really help me is to simplify this first ratio, because I know 54 and 18 are both divisible by 9. So if I divide both of these numbers by 9, I'm going to get 6 over 2. And that tells me that I actually could have divided them both by 18, because if I get 6 over 2, I know that that simplifies to 3 to 1. So instead of, if I don't have a calculator, instead of using 54/18, I could instead use the similarity ratio 3 to 1. That way, when I cross multiply, I get 3x instead of 54x is equal to 36. And then I could just divide both sides by 3, and 36 divided by 3 is 12. So 12 is the value of x that would make those two triangles similar to each other. All right, to our third and final similarity theorem. This is the side-side-side similarity shortcut or similarity theorem. If the lengths of the corresponding sides of two triangles are proportional, then their triangles are similar. So in this case, we don't know anything about the angles. And we don't need to, because if this is true, then the triangles are similar. And remember, this only works with triangles. So perhaps this triangle has sides 2, 5, and 4. And maybe this triangle has sides 4, 10, and 8. So without knowing the angles, and again, this only really works for triangles, I can prove that these shapes are similar. So if we look at this last example, using side-side-side similarity, which 3 of these triangles are similar? And they've been color-coded to help us identify the corresponding sides, but when I set it up, I like to think of it as small to medium to large, essentially. So we can look at these kind of one at a time. So I'm going to out here do small to medium to large, and I'm going to first look at triangles 1 and 2. So from triangle 1, I have 6, 9, and 12. And for triangle 2, my smallest side is 4, my medium side is 6, and my longest side is 8. So for these to be true, these all have to be the same ratio. So if I simplify this, 6/4 simplifies to 3 halves. 9/6, I could divide both of those by 3, simplifies to 3 halves. And 12/8, I could divide both of those by 3. Excuse me. So if I could divide both of those by 4. Sorry, I lost my train of thought for a second. Dividing those by 3 won't really help me. So if I divide both of those by 4, I get 3 halves. So all 3 of these ratios for 1 and 2 simplify to 3 halves. So we know that 1 and 2 are similar. Now it's possible that triangle 3 is also similar to them. So I only really need to test it against one of those triangles, since I already proved 1 and 2 are similar. So I'm going to look again at the small, medium, and large sides. And I'm going to look at maybe I'm going to compare triangle 2 to triangle 3. And again, it'll be similar if they all reduce to the same ratio. So for the small side, for triangle 2, that's a 4. For triangle 3, that's a 6. The medium side for triangle 2 is a 6. For triangle 3 is a 10. And the long side for triangle 2 is 8. For triangle 3 is 14. So I need to simplify these ratios and get the same thing. So the first ratio, I can divide out a 2. I simplify to 2/3. The second ratio, I can only divide out a 2, and that simplifies to 3/5. So I don't think they're going to be similar. If we just check this last one for fun, I could divide out a 2 and simplify that to 4/7. So triangle 3 is not similar to triangles 1 or 2. That's the end.